Well, hi, good morning. Thanks so much for coming and joining me here in my shop today for day 2 on this radio. I think what I want to focus on right away is at least one key capacitor in this radio that could affect the operating life of the output tube. Output tubes are generally expensive. This one not so much. I think this is an EL84, so it's not such an uncommon tube, but nevertheless you don't really want it wearing out prematurely. So there's one capacitor that, if it's leaking charge, can result in that tube's early demise without even knowing it's happening while you're listening to the radio. So let's go hunting for that tube. I think the first place we should go is the schematic and find it. Did I say tube? I meant capacitor. Okay, so we're looking at the schematic here. This is the output tube. Its output goes into the output transformer, where it then heads off to the speakers. The speaker and the electrostatic speakers, which I guess we'll be talking about somewhere down the road when we get to that. Electrostatic speakers are not driven out of the output transformer. They're driven more directly. We won't get into that. The issue here is this tube's grid. So there's this grid right there on pin number 2. You see it says 0 volts. 0 volts relative to the chassis. And all that's going on with this grid is a little 1000 ohm resistor here, a big 1,000,000 ohm resistor going down to the chassis. And then the signal being applied to this tube is coming through this capacitor too, from the output of this tube. You can see the plate voltage here is 70 volts. We have 70 volts here, and we have 0 volts here. What happened to the voltage? The voltage cannot get past this capacitor, or under certain circumstances, the two of them. So you can see there's a switch here. It says voice on top. This is just another German tone control here. I don't know what it is about German engineers and their tone controls, but they just go wild in these radios. So here's a switch you throw, and it gives you a tone quality that's good for listening to people talk, good for voices. You throw the switch up, now the signal must pass through this capacitor, and through this one, and through this resistor to get all the way to the grid here. And when the switch is down, the way it is now, this capacitor is actually shorted right out. So this one becomes the lone capacitor. Now this guy's job is to stop the voltage, but let the signal go through, the alternating current signal pass through it. What happens with this particular capacitor in a circuit like this is over the years it degrades, and it can't block DC as well as it could initially, and there's a small leakage going through it. In other words, this is becoming a very large resistor. So if you leak enough charge through here, and you have a 1,000,000 ohm resistor to fight through to get to ground, some pressure is going to develop here. And you don't want that there at all, especially because it's actually the reverse of what you'd really like on a grid. Grids should be negative relative to the cathode. I'll explain how that's done in this tube in a moment. And if there were some extra electrical pressure making this more negative, well, it wouldn't really hurt this tube. I mean, it might ruin the output and make the radio sound terrible. Wouldn't really hurt it. But what if it goes the other way? What if the grid is somehow made positive? This presents lots of problems. Increases the current flow through the tube, causes a grid current to flow, which is not welcome. Probably result in distortion when it gets bad enough. The extra current flow through the tube wears out the cathode prematurely. These tubes, output tubes, are hard-working tubes. They run hot because they have to deliver a lot of current, so they're designed to do that. The economics says it makes more sense to design this tube with a limited life and expect a replacement during the life of the radio. These other tubes are not working nearly as hard in the radio. These ones up here, these signal tubes and that, they're not working very hard. They tend to last longer. But these ones tend to wear out with use. And then if you have this problem of this leak here late in the life of the radio, this grid gets a little bit, it doesn't get really positive, it gets less negative is what's happening. I'll explain that in a moment. And you get more and more current flowing through the tube, even without any sound. You just turn the set on, have the volume at 0, and there's extra current flowing through here because of the charge making it through this capacitor. And it's all invisible to your ear. I guess, is everything invisible to your ear? You can't hear the difference until it's kind of too late. So how do they get a grid bias on here? These tubes, like all tubes, need a bias voltage. This one I'm going to guess, I don't know what it is, but I'm going to guess it's 10, 15 volts, I don't know. So what they do is, rather than make the grid go negative, which is difficult in a radio that has no easily available negative voltage to use to push the grid negative, instead you let the cathode go positive. So if the cathode is allowed to rise up in voltage positively, then the relative voltage between the grid and the cathode makes the grid negative. So this is how they do it. They put a little resistor here in the cathode circuit. So you have the main current flowing through the tube, flowing through this resistor. There's a voltage drop on the resistor, and that causes the cathode to be a little bit positive. One of the problems with this is the resistor does has a couple of negative effects on the signal strength, let's put it that way. So you don't really want the signal passing through this resistor, so you bypass it and you make a path around it with a large capacitor. Look, this is really large, 50 microfarads. This one is 0.025 microfarads, so this thing is like 1,000 times bigger. This is a much bigger capacitor here, and the signal will happily, this is not a really high resistance here either, so you really need a low impedance here for this to work. So you have a very large capacitor here, and the signal will use this path to get around. It won't go through the resistor. So what we can do here is we can operate the radio and test the voltage on this grid with a voltmeter and see if it's 0. If it's 0, if it reads 0, then there's no significant charge leaking through here. But if it doesn't read 0, if it reads +1 or something like that, then this is already beginning to leak. And the bias that's developed through this cathode resistor will be diminished by the voltage that's being created by the charge coming through this capacitor. That's the deal. So we got to find this tube, find this grid, make that test, find this capacitor, change the capacitor, and repeat the test and see what we get. Pin number 2 on the EL84. Okay, that's where we're heading. Okay, let's go looking for that capacitor. Now, just looking for the pointer here. So you can see my camera there. We're looking right in at the output tube. The output tube is right down here. So let's switch to that camera. We get a little closer look at things. Yeah, okay, which one? Lots of parts in here. So the kind of capacitor I am suspicious of that we are looking for is something like this brown one here. There's another brown one here. There's one here. Hey, there's one hidden away. Oh! How much you want to bet that's the guy right there, too? So the way we can find it is by counting from the find pin number 2 on the tube. Yeah, pin number 2. So I'm looking for the gap. I think it's down here. No. Maybe it's right under this resistor here. Right where I'm pointing. Yeah, I'd say this is the gap. Okay, so we start counting from here. Wait a minute. Looks like pin number 1 is no connection. Pin number 1, 2. This is pin number 2. So we find 1,000 ohm resistor. Brown, black, orange. Well, is that red? Maybe that's red. Sure looks orange, doesn't it? If it's red, it's 1,000. So let's assume that's 1,000. From pin number 2, 1,000 ohms, comes over to this terminal. And off it is that capacitor, this one here. It's a fairly large looking one. Now, can I read the size on that thing? Offhand, no. It's kind of buried under there. Comes over to this terminal where it should find another capacitor. Oh, there's a big one. It's supposed to find a small one. A little bit of dust in there. Supposed to be a small one, I would imagine, a mica one. Let's go again. Come through here. I think this is 1,000. Comes to this terminal. Connects to definitely this capacitor here. Many other connections. There's another resistor here. Not many other, just one other connection. One other connection. And the other side of this one comes around to here. So we have this. This, I believe, is a tiny capacitor, but you know what? I'm not sure. I'm still. Sometimes these are resistors that look like this. I have this fairly large capacitor here. 0.1. I can read it. This one's a 0.1. So what's a 0.1 doing connected? This could be a ground point. No, it can't. It cannot be a ground point because the job of this capacitor, if it's the one I think it is to convey the signal, and it's not grounded at either end. Okay, let's look at a diagram now that'll point to one of these capacitors and tell us which one it is. So we'll go back to our schematic here. So we're looking for C59. C59, and we might want to keep an eye open for C55, and maybe even C3 if we spot that. Okay, C59. Now we're going to flip to some other diagrams here. Those are resistors. That's not it. How about this one? Here we are. C59. Oop, there it is. C59. Pointing. So the capacitor. Wow, this is hard to look at. So there's the terminal strip. Here's the resistor coming over from the grid, connecting to a terminal. Now there's two capacitors right in that area. There's the one I think it is, and the bigger one. But this is supposed to be a point. So how do you get? So what would the other one be? The other one would be C59. 59, isn't that what we're looking for? Oh my gosh, I'm lost. 59 is what we're looking for. 55 is a small one nearby. Where's there a 0.1 in this deal? Somewhere around here. There's a 0.1. Way over here. That's probably it. That's probably the 0.1 we're seeing. Well, but it seems to be right on. Look at this. It's grounded on one end. Grounded on one end. The other end's between resistors. It doesn't make a connection over to this capacitor at all. This capacitor is connected to this resistor. We should be able to find this 1 meg also. I find it's very important to be absolutely sure. Be absolutely sure of what you're doing. Because first glance, you get these things wrong so easily. And an optimistic attitude, you tend to see things the way you want to see them instead of the way they are. So how's this work? There was that little, what I think is a capacitor, hooked up here, but there was more coming off here. And something that always makes me nervous is that the schematic I'm looking at is actually not completely correct. I don't think that's the case here. But the fact is, the radio we're looking at is that. Why is it saying? It says Olympic, Opta, Bella Luxus. What's this Olympic? Olympic Opta. This is a low Opta. Olympic Opta. Well, I've never heard of Olympic Opta. Might be Mr. Lowe sold out to Mr. Olympic and they took over the company, half the company. I don't know what's going on there, but that kind of thing makes me think, hey, maybe this isn't quite the right schematic. I have no really hard evidence of that, though. So 1,000 ohms, 1 meg, 59 is showing up where this arrow is pointing. 55, yeah, it's 55. That's the 0.1, wasn't it? Mr. Short-Term Memory, 56. 56 is the one. 56. Yeah. Oh, there it is right there. You can see it. And that's definitely that big one. Now, there's 2 of those brown guys over here. There's one I think is the right one. And there's another one just beyond it. So we have 59 and 52. And what's 52? 52. Way over here. Oh, it's another similar blocking capacitor. Blocking on the grid of this. This may be another one we have to get at anyway. Okay, so 59 is a 0.025. Let's just see if we can find this 1 meg resistor, and that'll kind of verify everything. Okay, back to the radio. Gap 1, 2, resistor, 1,000. Red looks like orange. And then off of here is another much larger resistor. Well, there is one right here. And that one is a what? That one can't quite see the color here. It's a green, 3rd band. Looks like brown, black, green. Brown, black, green's 1,000,000 ohms. Like creaky lights. Okay. That's got to be it then. This has to be a 1,000 ohm resistor, even though it doesn't look like it. Everything's adding up. That's the capacitor we got to get to. Lead comes. It's so easy to be fooled in these radios. Get on the wrong lead, the wrong component. So pretty sure that's the lead. And this is obviously the other lead. Looks like I can nip it here and pull it out downwards. Yeah. Okay, we're going to do that. Now I don't know for sure that this capacitor is leaking. Seriously, I haven't taken any capacitors out of this radio yet. I'm cutting the right lead and only one. Cut this here. Out that capacitor. I hope it says 0.025. And what does it say? It does not say 0.025. No, it says 0.022, which is just as good. The condition of it is very, very good. I'm looking at the end seal. If you used a black tar material, a lot of these, this might be an upgrade from earlier versions of this capacitor, where the material sealing the end was just kind of a brownish material. I think this is probably an upgraded version of these. How would you want to bet this guy tests pretty good? We're going to find out right now. Let's go to the other camera. So one of the things I like to do is test the components I remove, so I have, again, some objective truth about what I'm doing and what I'm thinking, rather than just get in there and willy-nilly start changing capacitors left and right. So this is a capacitor checker. It's intended for, it's from the vintage era, so it's intended for exactly what I'm going to do with it. I'm going to clip this capacitor on here. Now I've fixed the focus on the camera you're looking through, so I got to make sure it's the appropriate distance. That looks alright. So, the secret here, get rid of unnecessary cords, is this magic eye. A little hard to see in the camera today, but the eye is bright all the way around, but there's an open quarter down here where I'm showing my fingers. It just looks a little bit darker down there. When I hit the switch here, the device is going to put 50 volts onto this capacitor, 50 volts DC. If no current leaks, the eye, after shutting for a moment, will open up just like this. It'll look just like this again. Let's see what happens. So now it's opened about 3/4 of the way. You know what I forgot to do? I forgot to test the radio with this capacitor in there. Oh, what a dummy. What a dummy. 150 volts, it is not passing the test, so to speak. So, brand new capacitor, like what I'm going to put in there, you can test it up to 450 volts and this eye will pop right open. There's no leak whatsoever. So, in a sort of a qualitative comparison, this is a very leaky capacitor. Almost certainly this was causing a rise. And how stupid of me not to test the radio. What happened to my plan? I really can't put that back in there now, and that just doesn't make sense. Too bad. Missed a great opportunity here to sort of demonstrate the effect of something like this. That's too bad. Now all this beautiful seal, and still it's a little bit leaky. And this is a very sensitive location. You know, a little bit of leak in a capacitor is not going to do something bad in most cases, or in some cases. In other cases, a little leak, very bad. So we're going to put the new capacitor in there. I'm afraid there won't be any change in the operation of the radio that we can notice now. Although I can always do the test after, but there won't be any voltage there. Okay, I'm going to install that capacitor and be done with it. Okay, you can see the yellow capacitor in there. Let's just make sure the connections are solid here. And I don't know if I can get on that piece of wire. Sure it is. Okay, one capacitor done. Now, let's go back and take a look at the schematic. See if we can hunt down some more critical capacitors. I'm just still kicking myself in the rear for having not done the grid voltage test. Drat. Okay, let's see what else we can find here to fix. Okay, you know, we're not done yet with the output tube. We should really check this resistor. In many radios, this resistor runs warm. It's carrying a fair bit of current. Sometimes this is a higher wattage resistor here too. And because it's running warm, it has a shortened life in many radios. Resistors tend to go up in resistance, so as this thing goes up, the bias relationship between the cathode and the grid gets bigger and bigger, and the grid appears more and more negative. And I would imagine that eventually you just can't get any volume out of this radio. I don't think it's a damaging thing in itself. So we need to find this. Now 150 ohm resistor, that's brown, green, brown. Brown, green, brown. Maybe a different wattage or a different type of resistor right around this tube. And that should lead us to this, which I think I'm looking at anyway. I think it's pretty obvious. This capacitor here, which is also something of consideration. You don't want this to be weak, but it probably isn't weak in this radio. So let's go looking for this resistor. Okay, where are you? So we're looking for brown, green, brown. I see it already. I do see it already. Brown, green, brown. There he is there. And could be it's a little bit of a higher wattage resistor than all these other ones here, on the style of it. And I'm pretty sure this capacitor back here is the bypass. It says 15 volt rating on it. We can't see the size. The rating is only 15 volts. Gives you an idea of the cathode bias voltage level that's expected in the radio. Probably 10, somewhere around there. And so is that capacitor hooked up to the same terminals? See the black cover coming here? Yep. Right to this terminal with the resistor. The other lead. The other lead could be going to a grounded terminal. Looks like we can't be absolutely sure. It's just disappearing from view down here. This is the positive end. You can see the positive up here. And that's on pin number 1, 2, 3. Pin number 3. Okay, so I'm just going to peek at the schematic myself. And this is again just along the lines of making sure things are adding up. Pin 3 is the cathode pin to which that resistor and capacitor should be connected. So there we are. So that's the cathode resistor and that's the bypass capacitor, and they both look to be perfectly fine. Looks can be deceiving, but I bet you they're not. What we'll do, we'll take a little resistance reading across that. Oh, you weren't looking at the schematic while I was talking about it. Okay. Oh well. Just rack it up to bad video making. Okay. Well, I think I did mention, didn't I do these things mostly live? so you get to see lots of my mistakes and stuff, including even how I operate the video itself. So here we go. Get my Allen meter ready here. And we'll want to measure resistance, and we think it's around 150. Around 150. Here we go. With it still in circuit, I think it's okay to measure. And we'll see. I think this is it there. 147. And it's supposed to be 150. So there's nothing wrong. So that's just fine. So that'll create the proper cathode bias, or effectively the grid bias. Keep the tube running in its linear area of operation. And get maximum life of the tube, especially since that other capacitor has been changed out now too. Okay, let's see, that might be it for today. Maybe today is all about the output tube and making sure it's not being abused by the radio. Now we've taken out one of these kinds of capacitors and found it to be a little bit leaky. Would that be the case of all the remaining capacitors of that type? Quite likely. They're quite likely all in the same condition. So exactly how to approach this without doing a whole pile of unnecessary work and without doing taking on a whole pile of risk and fiddling around with this radio and then messing things up, I got to think about which of these would be worth changing out. And perhaps none of them. Perhaps none of them at this point. Okay, that's great. Okay, one more thing I should do if I want to close the book on the output tube, and that's test it in the tube tester. Now, it certainly seemed to be loud enough and good enough. Let's pull it out of here. EL84. So I'm looking for black staining on the inside of the glass, deposits that have been building up. It seems a little darkened up in here, but I don't think that really matters. Just in this clear area. Looks good. Doesn't show any signs of wear, but again, all those things are non-conclusive observations. Hey, there's the tube tester. So I have a listing of European tubes for operating this tube tester. And I've set this up for an EL, just have to make sure, EL84. I'm going to double check these now while you're watching. It's always good to double check this stuff. EL84, so 6.3 volts. Wow, okay, got that wrong. 6.3 volts on the filament. EV2793. EV2793. 0. There's no suppressor grid in this tube. And 23 on the bias. It's good. And 90 on the English. We're set not on the English. We're set on the 3000 scale here. So this tube tester will measure, I guess you could say, the tube's ability to amplify. It's not quite the right way to put it. There we go. What it actually measures is something called the transconductance. The tube can be thought of as a inside-out resistor. Kind of. You put more voltage on it and the current gets less. You can kind of think of it that way. It results in this, considering the translation of what's happening between the grid and the plate, gives you a value or a number called mutual conductance, or GM. You can see the word GM there. Well, that was just a horrid explanation. It didn't really explain anything. Okay, first we need to operate the short switch and see if there's any shorts. So we're watching the light here. Looking for internal tube shorts, which is not likely to be in there because the radio's been operating. Okay, so this one, to make that measurement, we push the P4 and there's a value that we need to look for. Just let me just get it in my head here. The value is 3600, throw it away, 5800, applaud. Applaud at 5800. So we'll put this up to the 6000 scale. So a good tube should put this meter all the way over, almost to the end of the run here. And a tube that's ready for replacement, 3600, well, that's roughly in the middle here, right? It's right around here. So we're hoping it comes up in this area. Ready? Here we go. So it's way up there in the good. Well, I shouldn't say that. We're not reading good and bad right now. We're reading the actual value. So the actual mutual conductance as measured with this tester, and the way it does it, it resolves, looks like 2250. Very good. Okay, no problem with that too. It's gonna last for years under, say, occasional use. It's going to last longer now that that capacitor got changed. But of course, we don't really know because I didn't do the grid test. Jim, you really missed an opportunity there. Okay, put this tube back in, and I don't think I'm going to operate the radio. That's it for today. The situation with the output tube is good all around. Excellent. Okay, well, thanks a lot for watching. I am heading outside now to enjoy the very fine weather we're having. Hot sun, cool air, can't beat it. Thanks a lot for watching, and I'll see you tomorrow.